In this video, I'll be talking about the relationship between electric potential, electric field, and work done. So let us consider that this is the electric field, which means this side you might have a positive charge over here, or it might be due to a positive plate and a negative plate. So, so this direction means, let's say you have a positive plate here or negative plate, or it could be due to a positive wire here. So the electric field could be generated from different sources, and you have a charge, let's say this charge A, this charge Q, which is at a location A. And now our goal is to find out how much work is done if you move the charge from point A to point B in this electric field. So first we'll find out the amount of work done. If you recall the work done, how do you define the work done? The work done is defined as a force. The work done is defined as a force times dr vector. Let me write down here. The work done can be defined as a force dot dr vector, and this dot is the scalar product. It's not the simple multiplication, it's a scalar product. That's how we define work done. And this integration means we integrate from point A to point B. That's how the work done is defined. So if you look by that definition, that this is the work done. That's the work done. And AB means the work done in moving a charge from point A to point B. That's what it means here, in going from point A to point B. And this force, the force acting on a charge, is defined as Q times E, where Q is the charge and E is the electric field. That's how you define the work done. So if you know the electric field, then we can calculate the amount of work done. Now, if you look for a conservative system, such as a gravitational field, electric field, magnetic field, those fields or those systems are the conservative system, which means the work done in moving from point A to point B. Let's say you go from this point A to point B in a conservative system. It doesn't matter which path you follow. It could be this path, it could be this path, it could be this path, or it could be a straight line, any path. It doesn't depend on the path you choose. It only depends upon the initial position and the final position, or in other words, the straight line between them. It doesn't depend upon the path. Those sort of system or those sort of field we call the conservative field or conservative system. And in a conservative system, the change in the potential energy, this is the potential energy. U stands for the potential energy. So U here means the potential energy. Let me write down PE, potential energy. All right. For a conservative system, the change in potential energy is equal to the negative of the work done. Okay. So now we're going to define the potential difference between these 2 points, point A and point B. So the potential difference between these 2 points is defined how much the potential energy changes divided by the charge. That's the potential difference. So if you have calculated the potential energy, how much potential energy, there's a change in the potential energy, how much potential energy has changed, and if you divide that by the charge you're moving, and that gives you the potential difference. So now let's take this, try to simplify this equation now. So the change in potential energy, this is the change in the potential energy. Now if you look at this one, the change in this potential energy is equal to the negative of the work done. So here I'm just simply replacing this one by the negative of the work done and divided by the charge which is already there. And thus this is the work done. And if you look at this equation, the work done is simply equal to the integration of a to b f times dr. Then just plugging this equation here. And also the force is equal to q times E. So the electric field would be simply equal to force divided by Q. So here you have force and divided by Q that we can call as an electric field. So we got this equation. So this is a very important relation. This is important relation because in the coming lectures we'll be calculating the potential difference in different sort of electric field, or we're going to find out the potential due to a charge or charge distribution, and the relation you have to use is this equation. So let me try to explain a little bit more. Now let's say you are in a uniform electric field. When I say a uniform electric field, you can achieve or you can get the uniform electric field between the two charge plates. Let's say you have a positive charge plate and a negative charge plate. If it is sufficient long, then the electric field between the two plates is uniform field. If this is uniform field, then the E, you can take it out because it is a constant field. And then you simply have to integrate the dr, which is the displacement. And in this case, let's say the displacement is from this charge plate A to charge plate B. Let me write down here, this is the plate A and this is the plate B. And then the location would be the simply RB minus RA, which is the distance between the plates. So what we have found is the change in the potential. The change in potential is equal to negative of the electric field times the distance. Or in other words, the electric field is equal to negative of the change in potential divided by the distance. So this is again a very important relation, because in many numerical problems you will be using a charge plates where the potential is given, the distance is given, and then you're going to use this relation to find out the electric field. And the one last thing I would like to mention here, so sometimes it is we cannot see electric fields, but in our daily life we are so much accustomed with using the gravitational field. So there is nothing difference between the gravitational field and the electric field. You will get the same sort of relation. So what I'm trying to say here, let's say you have a mass on an inclined plane. If you roll down this object, what is happening here as the height is decreasing, the potential energy is decreasing. At this point, the potential energy is zero. At this point, what we have here is the total potential energy. And if you need to find out work done, how do you define the work done? The work done in this case will be equal to the change in the potential energy. So again, even in this case, the change in the potential energy will be exactly equal to the negative of the work done. Okay, so if you move an object downwards, the potential energy is decreasing. That's exactly the same age here. If you move this charge from point A to point B, this is exactly equal like from positive plate to the negative plate, which is just like rolling down on an inclined plane. That means the potential energy of this charge is the decreasing, because you are going from the positive plate to the negative plate. That means you are rolling down an inclined plane if you think in terms of the gravitational field. So in conclusion, I would say this relation and this relation is so much important to for the upcoming lectures videos. This is